and I'll drop little amounts of that base in there. And what's going to happen? The neutralization reaction. At this point, we have the maximum buffer because what's in there? We've got weak acid and then we've got conjugate base. Now I'm going to show you what this is, what we actually did. This time, instead of a strong acid, I'm going to use a weak acid in my beaker or flask. I'm going to put a pH meter in there. I'll put a strong base up in the burette and I'll drop little amounts of that base in there. And what's going to happen? The neutralization reaction. And what we're going to do is we're going to plot that pH versus volume of base added. And what will that pH curve look like? Well, it's a little bit different. This is one that I did. I used a weak acid of acetic acid and I titrated with sodium hydroxide. And so what I'm doing is every time I measure the volume that I'm adding, and then I'm measuring the pH as it goes. And you'll notice it does still gradually increase and then it's going to go up. But it is at a different location, okay? And so this one starts off really low and it's just going to go along, kind of gets a straight line right here, and then all of a sudden it will shoot up, okay? Now remember the special point, okay? This point right here is what we call the equivalent point. And this is when, what is true, do you remember? Moles of acid equal moles of base. Notice we're not at a 7 here, we're a little bit higher than that. So this is different, okay? The other thing that you're going to notice, it's more of an S curve, I would say. So instead of just a steep line, like we have a strong acid and base, there is more of an S, okay? So more of an S curve, it's less steep. And then the other thing that we're going to notice is that we have a straight line at the bottom, okay? So lower pH. Now, let me show you how this works. So if you take your volume here, I can tell that my volume here was like maybe 7.5. So this is the volume of the base needed to react with all my acid. Well, what I want you to do is take half of that volume. So half of 7.5 is, 3 point whatever. And so I'm going to go to that point. Let's see, 7.5, half of that would be like 3.7. So I'm going to go to that point on my graph and I'm going to go up. So take half of the volume, all right, so multiply by 1/2 and you go up there, and what you're going to get is something really special. Guess what that's called? The half equivalent point. Okay, and at this point, something is really interesting here. We have the moles of acid in the solution are equal to the moles of the base at this point. And so this is what we call the half equivalent point. So make sure that you can pick this out. Also, you're going to find out that this is also related to the pKa. So we'll get there in a minute. Maybe you can figure that out. So this is what we have the maximum buffering. I'm going to just write that out. At this point, we have the maximum buffer because what's in there? We've got weak acid and then we've got conjugate base. So this is the maximum buffering. And the reason that we're poking along so long with this pH low is because we have a buffer solution. If it weren't a buffer, the pH would be changing very rapidly. Okay, and by the time you get up to this equivalent point right here, guess what? You're out of buffer solution. And so when you start to add base, that pH goes shooting up really, really fast. All right, let's do a quick problem with this. All right, what was my initial concentration of acid? Let's find that. So I know how much base. I have a volume of base, and I have the concentration that I put into my burette. So I've got 0.04 liters of base, and the concentration was 0.25 moles of calcium hydroxide per liter. Okay, that's 0.25. All right, now I want to flip this thing over to moles of acid. So I'm going to say moles of acetic, okay, for moles of calcium hydroxide. Now, it's important to write that neutralization reaction because look at this. All right, look at my coefficients there. 2 moles of acetic for every 1 mole of calcium hydroxide. Don't skip that step because your answer will be off by a factor of 2. All right, so that will get me 2 moles of acetic, and then I know my volume, so I'm going to divide by 0.0300 liters of solution. All right, let's check units. I've got liters of calcium hydroxide, cancel. Moles, cancel. I'm going to end up with moles of acetic per liter. That would be the concentration, okay? So all I have to do is gather up the numbers, 0.04 times 0.25 times 2 divided by 0.03, and that's going to give me 0.67 molar acetic acid. Now I'm going to show you what this is, what we actually did. So that is the concentration of acetic. So if I go back to this initial, so I have an unknown concentration of acetic, right? And I put my known concentration of strong base in the burette. Drop it in there, plot this curve, guess what I get? The actual volume, and then I calculate the unknown concentration of acid. All right, that's pretty cool. It's pretty cool in the lab. Also, you need to be able to work problems like this. Take your time, show your work. It's just stoichiometry.